Hi everyone, I am Lynn Clark and I make code cartoons. I also work at Mozilla. I work in the emerging technologies group there. So that's things like the Rust programming language, and Servo, which is an experimental super fast browser engine, and WebAssembly. But I'm not going to be talking about those things today. Instead, I'm going to be talking about React Fiber. I'm going to start from the very basics and explain what Fiber is and how it works. But before I do that, I want to show you what it does. Here's an example of a React app. On the left, you see React as it is today, and on the right, you see React with Fiber. This is a toy example. It's not really a good example of an app that you might build, but it is a good stand-in for other apps. And I'll explain why it's a good stand-in later. But for now, I just want to point something out. Notice how on the left, you see some jank. You see some parts where the movement isn't very fluid. And on the right, it's moving more fluidly. So what does Fiber do? It improves the perceived performance and responsiveness for complex React applications. Now that you've seen what it can do, I want to explain what it is. Fiber is the new reconciliation algorithm for React. That terminology, reconciliation algorithm, may be new to some of you. So I'll explain where that comes from. When React first came out, the killer feature was the virtual DOM. The reason that was a killer feature was because it made coding user interfaces so much easier. Instead of having to tell the browser how you wanted it to change things in response to an event, you could just tell React what the new version of the UI should be, and React would figure out how to get there. It turned out that this way of handling changes in a user interface was useful not just for the DOM, but for other ways, for other user interfaces. Things like native apps on phones, or virtual reality, or even hardware, or terminals. If React was going to be able to handle these other use cases, though, the part of the virtual DOM that figured out whether or not there were changes in the UI was going to have to be factored out from the part that actually painted those changes to the page with DOM nodes. This introduced a formal distinction between the reconciler and the renderer. Renderers are pluggable, so you can take a renderer that's not in core, that's been created by somebody out in the community, and use it to target a different host platform. But there's only one core reconciliation algorithm. That's what you download with React. This is why Fiber is such a big deal. Over the past year, React's core team has been redeveloping this core algorithm from the ground up. And the end result is the Fiber Reconciler. Let's go back to this demo and see what it is about Fiber that makes this possible. There are two different things that are going on in this demo. The triangle is getting narrower and wider, and also every number inside one of those dots is being incremented at the same time on every second. This is a good stand-in for other apps because it makes very visible the interaction between different kinds of updates, high priority updates and low priority updates. The typing is high priority. When you're using an app like Facebook, you want people to be able to see the letters coming up as soon as they type them. An example of a low priority update would be data coming in from the server, like updating the like count on something like Facebook. Let's look at the mechanics of this example. At the top level, there's an instance of a triangle component. And there are more triangle instances under that until it becomes so small that you can only fit one circle in it, and then that dot is placed. The two updates that are happening here touch different parts of the instance tree. The update that's making the triangle narrower and wider is only touching one instance, that top-level instance. So it doesn't need to do much work. But it does need to happen frequently if it's going to look like fluid motion. The other update, which changes the number in each one of the dots, does take a lot of work. It has to go through the whole tree and touch all of the instances. But it's less time sensitive. You're not going to notice if that number is incremented right on the second or maybe 200 milliseconds later. So let's look at this chronologically. In order for the narrowing and widening motions to look smooth, these updates need to be happening 60 times per second, about 16 milliseconds per frame. Now, you may think that the answer is to make React faster. But the problem isn't really that it's hard to fit this one, touching this one instance in that 16 millisecond time frame. Instead, the problem is the fact that the narrowing and widening updates get trapped behind the larger updates that have to touch every single instance. And the time that's spent in these updates isn't really that much in React itself, but actually in the component code. So making React itself faster won't necessarily make this small enough so that you don't have this problem of jank. But there is a way to solve this problem, and that's to make the updates play together better. And it's not just updates within React that need to play together better. It's also updates that happen outside of React, things like CSS animations, or if you have a browser resize. And that's because of the way that the browser works. I've talked about this before, but your code is kind of like a project lead trying to build a website. Unfortunately, it only has one employee. It only has one worker to do the work, and that's the main thread. The main thread is like a full-stack developer. It's working on JavaScript, the DOM, and layout. And the time that it spends working on any one of these things, like this JavaScript doing this update, is time that it can't spend doing other things, like layout. I've said this before, but using React is kind of like introducing a technical lead to the mix. React helps your code work better with the main thread. It knows how the main thread works. And it does this by minimizing and batching DOM changes. What Fiber does is it teaches this technical lead some basic project management skills, like how to split up work and how to prioritize work. And it also gives this technical lead a watch so that it can keep track of the time. So how do these new skills come into play? How do they change the way that the reconciler works? Let's start by looking at how the existing reconciler works. This is a diagram that I've used in explaining it before. On the left, you have elements. These are what you give to React to tell it what you want it to build. So these are returned from a render function. The instances are what React creates internally so that it can manage its work. It uses these instances to compare the previous version of the app to the next version of the app and figure out what changes it needs to make. And then the DOM nodes are what React creates in the browser to make layouts happen. With the existing reconciler, this is built up layer by layer. So first, React will create the element for the thing, and then the instance, and then the DOM node. And to do this, it will recursively call mount component or update component for each layer until it gets down to the bottom. If you record a timeline of this in your browser's DevTools, you'll actually see a graphic representation of this. You'll see a call stack that has recursive calls to mount component or update component and just keeps going down. This stack also shows us what the problem is. The main thread gets stuck deep in this call stack, deep in this recursive call, and you have no way to get out. If you want to be able to jump in the middle and do some other work, you need to be able to break up the stack into smaller pieces. You need to let the main thread come up for air and check to see if it has other work to do. Fiber does this. It makes it possible for you to compute parts of the tree separately, and then to shift gears in the middle if the main thread needs to do some other work. The way that it keeps track of where it is in this tree is through a data structure called a fiber. And incidentally, that's where the name comes from, the fiber reconciler. It's because of this data structure that it uses to keep track of where it is. And so the old reconciler has retroactively been given the name the stack reconciler because it uses the call stack to figure out the same thing. The fiber is just a plain JavaScript object, and it has a one-to-one relationship to the instance. It manages the work for the instance. The fiber keeps track of its instance using a property called state node, and that points to that instance that it's managing. It also keeps track of its relationships to other fibers. Now, it's easier to understand these relationships if we walk through an example. So I'm going to use a user interface that I've used before. It's a list with a button, and when you click the button, all of the numbers in the list are squared. This only requires a handful of components. You have the list component, which renders to an array of elements. First, an HTML button, and then 3 items. You might be a little bit confused about the array there, and that's because currently React cannot accept arrays, so you can't return an array from render. But with the fiber reconciler, you will be able to return an array of elements from render calls. The first fiber in this tree would be something called the host root. That corresponds to the container that you inserted your React app into. The child of the host root is the list that we were using. And there's a link between them called child, and then another one back up to the parent called return. The children of the list have more interesting relationships. The button has the same child and return relationship, but you'll notice that the second child, the item, doesn't have that child relationship from the list. Instead, it has a sibling relationship from the first element, the button. Each of the sibling fibers will point to its next sibling, and that's how React is going to traverse through this tree. So those are the relationships that each fiber keeps track of: return, child, and sibling. There are some other properties that React keeps track of on the fiber, but I want to walk through an example so that you can have more of a context for what those properties are. I'm going to use the same example user interface that I showed before, but I want to make things a little bit more interesting here. Halfway through, the user is going to click a button that triggers an update, not in React itself, but in JavaScript outside of React. This button is going to increase the font size. That's going to require the main thread to do some layout calculations and some painting. And we'll see how that changes the way that we build the tree. Here's the diagram that I've used before for the stack reconciler. Because there's a lot going on in the fiber reconciler, I'm just going to show building up the fiber tree. I'm not going to show the elements or the DOM nodes. So just this middle part. Before we start the update, we already have the current fiber tree. And this was what was created on the initial render. React also started something called the work in progress tree and created the first fiber for that. The reason that we need a work in progress tree is that we don't want to make changes as we're going along. We don't want to make changes to the DOM as we're walking down this tree. Now, in the past, with the stack reconciler, that's what React would do. It would actually, as it's walking down the tree, be making changes both to the instance and to the DOM node for that instance. So for example, when React updates the instance for the second item from 2 to 4, it would also make that change to the DOM before it updates the instance for the third item. Now this works if you're doing all of the work in one pass. But if you need to interrupt this work, if you need to put it on pause so that the main thread can go do something else, then the main thread is going to paint that change out to the screen. It's going to change 2 to 4 without actually making any changes to the rest of the tree. And so your UI would be inconsistent. To avoid this problem, Fiber has 2 phases. The first phase, the Reconcile phase. In this phase, Fiber will figure out the work in progress tree and what changes are in that work in progress tree. But it won't actually make the changes. It's not until it gets to the commit phase that it will actually make the changes to the DOM. Phase 1, the Reconcile phase, is interruptible. You can pause and let the main thread do other things. But phase 2 cannot be interrupted. That commit has to happen all at once so that your UI doesn't end up being inconsistent. Our task in phase 1, the Reconcile phase, will be to fill in this work in progress tree and figure out the list of changes from it. Let's start an update to see this work in progress tree get filled in. We'll start by pressing the button, and there is a click handler on the button that we'll call set state on the list. This will create an update queue. And so this is just a list of updates that need to happen on this instance. Then React will go and schedule the work for that update. When setState was called, the app would have let React know that this change doesn't need to happen immediately. It can wait a little bit if needed. And because of this, React is going to schedule some deferred work. To do this, it uses a function that is built into many browsers called request_idle_callback. This is basically like React saying to the main thread, let me know when you have some spare time, and we'll take care of this work. For browsers that don't support it yet, it will polyfill request_idle_callback. When the main thread has some free time, when it's not actually building out a frame, it will come back to React. And it knows how much time it has before it needs to get back to all of the other things it has to do. This could be a few milliseconds, or it could be up to 50 milliseconds if it doesn't have any work scheduled in the near future. So now we'll start filling in this work in progress tree. We fill it in with a function called work loop. The work loop is what gives Fiber this appearance in the timeline. It allows React to go down and compute one fiber and then come back up and see whether or not its deadline is passed, at which point it would let the main thread get back to its other work. In order to do this, it needs to keep track of two things: the next unit of work that it needs to work on, and the time that it has remaining. So React in the main thread gets started. In the first pass through the loop, the fiber will work on the host root. They're just going to go and copy the values from the current tree over to the work in progress tree. And this includes a pointer that the host root has to its child. There are no updates for the host root, so React just starts processing the child, which means cloning the child fiber into the work in progress tree. And this is the list that had that update queue on it, so that is also cloned over. The list fiber will get returned to the work loop as the next unit of work, and React will come back up to check whether or not its deadline has expired. Because we still have some time, React will go back down and start processing the list. Now, the list does have an update queue, the one that we cloned from the current tree. So React will figure out the new state based on that update, and then that update queue is finished processing. Then the fiber is marked. It has a tag attached to it because it needs to have an update in the DOM tree. To move further down this tree, we need to know about list children. So React will set the state and the props on the list instance, and then it will call render. So the list instance will create the elements that it needs React to render and returns them. These elements, I think of them like note cards. They're basically something that your component can hand off to React to tell React what it needs to build. React goes through this array of elements and sees whether or not it can reuse fibers from the current tree. And since in our case it can, it will just clone all of those over. Then it returns the first child in the list, in this list of siblings, which is the button, as the next unit of work. So React comes back up and checks its deadline, and I think you can probably see the pattern that's starting to form here. So I'm going to make it a little bit more interesting. The user is going to click the button that's changing the font size. This adds something to the main thread that the main thread is going to need to take care of at some point in the future. But React still has time on its clock. Instead of immediately processing the callback that's waiting for it, the main thread is going to go down with React and start processing that button, that first button. The button doesn't have any children, and this is the first time that we've handled something without any children. So this is not going to be creating any new work. React can complete this unit of work, and that means comparing the old and the new to figure out if changes have been made to the DOM tree. But since there haven't been any changes to the button, we don't need to mark it as changed. Since there's no child, the first sibling is returned as the next unit of work. And this is the first item, which is the number 1. React goes back up to check its deadline, and there's still time, so it goes back down. And this will follow the same pattern as the list. But let's say that the item has a should component update. If the numbers are the same, we don't need to do an update. Since 1 squared is 1, should component update is going to return false here. This means that the item will not be marked as having a change, as needing a change in the DOM. Now, the precise detail of how this works when should component update returns false are still a little in flux, so I'm not going to get into those details. I'll just skip to where the item is completed. And then it returns its sibling as the next unit of work. We still have time on the clock, so we'll process the item. It follows the same pattern, except this time it doesn't return false from should component update. So it gets marked as having a change, as needing a change. And then the div is cloned and returned as the next unit of work. We still have a little bit more time on the clock, so we're going to process this div. The div does not have any children, so it's not going to create any new work. This means that we can complete this unit of work. We compare the old and the new and see that there is a difference between these two. The 2 needs to be changed to a 4. Because of this, it gets marked as needing a change in the DOM. And it also gets added to a list on the parent item. The item keeps track of everything below it, all of the fibers below it that need changes in the DOM. So we're going to add this to that list. Now, there's no next unit of work that it can return. There's no child, and it also doesn't have any siblings. So instead of returning a unit of work, it calls complete on its parent because it knows, since it has no siblings, that the parent has no other children. I mentioned that the div was added to the items list of changes, and this is the first time that we've added something to a list of changes. It was added because it has the marker that there's a change that's needed in the DOM, and also we completed it as a unit of work. Now we've called complete on the item, and the item has also been tagged as needing a change in the DOM. So the item will add itself to the parent's list of changes. And as part of that, it takes its own list of changes and merges that into its parent's list of changes. So this item adds the div to its parent's effect list. Now, effect list is what these lists of changes are called. And then it adds itself to the end of that effect list. And now that it's complete, it returns its sibling as the next unit of work. And we go back up to check the deadline. It looks like we've run out of time, though. So React needs to let the main thread get back to its other work. But React still wants to finish this job, so it uses request_idle_callback again to basically say to the main thread, when you're done with what you're doing, come back here so we can finish things up. The main thread goes back to its desk and takes care of the callback that's been waiting for it. And this may include doing a layout and painting new pixels to the screen as it does in our case. But notice that the content hasn't actually changed. Even though React knows that it's going to need to change 2 to 4 at some point in the future, it doesn't make that change yet. When the main thread is done with when the main thread's done with that work, it comes back to React. They start where they left off. The last 2 units of work are finished off in the same way, so they get marked as needing changes in the DOM, and they're added to the effect list, and then that completes all of the units of work below the list. Now complete can be called on the list itself. As part of this, it merges its own effect list up into its parents and then adds itself to the end of that effect list. Finally, when the list is completed, it can complete its parent. Now React sets this work in progress tree as a pending commit, and this is the end of phase 1. We've updated the work in progress tree, and we've collected a list of all of the changes that the tree contains. Now it is time for phase 2. Actually committing this work and making the changes to the DOM. React will check its deadline, and if there's time remaining on it, it will perform the commit. And if there's not time, it will use request_idle_callback again, and as soon as the main thread gets back to it, it will commit this work. So we're starting phase 2. React will go through the effect list and make the changes to the DOM, starting with the first fiber, which is the div from item 2, where we need to change 2 to 4. The next effect in the list is the item, which was the parent of that div. And in our case, there are no changes to the DOM for this. But if there had been a ref, it would detach the ref here, and then it would reattach it later. And React keeps going and updating the DOM until it gets to the end of the effect list. Now all of the changes that were calculated in phase 1 have been committed to the DOM tree. This means that the work in progress tree that we've just built out is actually a better representation of the current state of the app than the current tree is. So to fix this, React just flips these pointers around. And this means that in the next update, React won't have to create new objects for each of these fibers in the work in progress tree. It can reuse the old ones and just copy over values that it needs to. This is called double buffering, and it saves a little time on memory allocation and on garbage collection. Now we're almost done with this commit. React goes through each of the effects in the effect list one more time and does a little bit more work, and then it's finished. So this walkthrough has shown how breaking up the work into units of work makes React more responsive to browser events. And that's a nice feature, but in and of itself, it doesn't actually help us with the problem that we started with, which is where some React updates were blocked on other React updates. In order to solve this, we need to add a little something more, and that's priority. In the Fiber Reconciler, each update will have a priority assigned. At the moment, these are the different priority levels. So synchronous is basically the same as the stack reconciler. It happens synchronously. Task work needs to be handled before the next tick of the event loop. Animation work happens on the next frame using request animation frame. And then high, low, and off-screen priorities all use request_idle_callback like I was showing before. High priority should happen pretty quickly in order to seem responsive. Low priority work isn't as sensitive. It's for things like data fetching, where you're already spending a lot of time in the network anyways, so you won't notice 200 extra milliseconds. And then off-screen priority is for those things that are actually off-screen right now, things that are hidden or that are below the fold. You don't really need them right now, but it'd be nice to have them just in case somebody clicks the button that shows them or scrolls down. With these priorities, what we want to have happen is for higher priority work to be able to jump ahead of lower priority work, even if that lower priority work has already been started. Again, I think looking at this in context will help understand how these priorities work. So let's say in the last example, instead of having a font increase button, we had an urgent React update button. So the user would click the button, and this would put a callback in the thread's main queue. The callback will wait for the main thread to come back and take care of it. When the work loop hits its deadline, React will let the main thread get back to its other work, which includes taking care of this callback. So it will call the callback, which will call setState. Then React is going to add it to the list of updates. Because it has a higher priority than the other update, though, it's going to jump in line. Then when React starts work again, instead of starting from where it would have started before, from the next unit of work, it starts from that host root again. It starts from the beginning. So it will basically throw out all of the work that it did before on the lower priority update. React will get through the higher priority update and commit it, and then restart the lower priority update from the beginning. Now, I don't have time to get into the details of how this works, but I do want to answer two questions that might have popped into your head. One is about lifecycle hooks. Some of them fire during the reconciliation phase, and some fire during the commit phase. So this means that lifecycle methods might not fire in the same order that you're used to. In this example that we just walked through with the different priority updates, here's how component will update and component did update would work. First, the low priority update would trigger a component will update. Then the high priority update would butt in and call both component will update and component did update. And then the low priority work would be restarted. Now, in some apps, the code depends on there being symmetry between these two. But there's no guarantee of that kind of symmetry with Fiber. So to make sure that this change doesn't break apps that do depend on it, the Fiber team is working on a graceful upgrade path for this. Another thing that you might have wondered is, what if a whole bunch of high priority updates keep coming and butting in line? Your lower priority update may never get finished. When this happens, it's called starvation. One way that React tries to fix this is by reusing work when it can. So for example, if there was lower priority work on the tree that hadn't been touched, the higher priority update hadn't touched those parts of the tree, then it will reuse that lower priority work. And the core team is actively working on more approaches to solve this problem. So this is how the Fiber architecture will make React apps better in the near future. It makes updates play better together so that your UI is more fluid and responsive. And it does this by breaking up the work into smaller units of work, which can be paused so that the main thread can go off and take care of other tasks. And there's also a name for this idea. It's called Cooperative Scheduling. You'll see it in other kinds of software too, like operating systems. And at Mozilla, we're currently building this into the browser, into the actual DOM, as part of Project Quantum, which is something that we're doing to radically improve the responsiveness of Firefox. Beyond what cooperative scheduling does for React today, though, it also opens up new possibilities for React's future. For example, one of the trouble spots for React right now is startup, how long it actually takes for that initial render to happen. The problem in many apps is that to render a single tree, React has to fetch all of the components in a single file, then load them all, and then it starts building up the instance or Fiber tree. But this could be different. React can start building up the tree as components stream in. And Fiber makes it easier to do this and to do this in a smart way. Another thing that Fiber could make easier is handling work in parallel. If you add more workers than just the main thread, the work can go faster. But parallelizing things isn't always a silver bullet. There are efficient ways to run things in parallel and inefficient ways. Fiber makes it easier to do it in an efficient way by splitting up branches of the tree and doing work on siblings in parallel. This is another thing that we've experimented with successfully at Mozilla. Our new CSS style system, which was developed in Servo but is now being introduced to Firefox, actually parallelizes things kind of like this. And in our testing, a page that took 130 milliseconds to render before will take 30 milliseconds. So you can imagine what performance wins you might see if you could bring this same kind of thing to React. Unfortunately, I don't have enough time to talk about all of the possible futures that this brings. I wish that I did. But I think that Fiber sets React up for some really interesting explorations and performance wins over the next few years. And I'm looking forward to seeing what develops. So in closing, I want to say thank you to the React core team. They explained Fiber to me so that I could explain it to you. And thank you all for listening.